3.2, properties of solids. Now it says here 3.2 and 3.3. That's because I blend a little bit of 3.3 and 3.2. I still will talk about 3.3 separately, but 3.2 and 3.3, there's a little overlap. Alrighty. So property stuff, I've talked about property stuff before, where you need to know the properties of the different things and why they are the way they are. So we're focusing on covalent compounds. I will recap the ones we learned earlier a little bit, but you need to know the more new ones. Yes. And so when we're talking about covalent compounds, we think about our IMFs. We might think about our intras or any other forces. It really depends on what we're talking about. So an example of this is when we have general covalent compounds. The IMFs are breaking, so we have those interactions between two molecules or more, obviously, and they break when they become vaporized, so going from a liquid to gas. This will relate to vapor pressure and boiling point, which again relates to the strength of the IMF. So we have three examples real quick. We got water versus two different alcohols. We have methanol with the formula there and ethanol with the formula there. Oh, I put a J there on accident. Oh well, whatever. And so if we look at the structures of these, here's water on the left, methanol in the middle, ethanol on the right. The red ones are the oxygens, the white ones are hydrogen, and the gray ones are carbon. And so if I think about what IMFs are here, I have my hydrogen bonds on all of them. Water has hydrogen bonds between different molecules of water. If I have methanol, pure methanol, then it would be the interactions between that OH to a different OH. Same goes for the ethanol. It's that OH group, right? And so if I'm thinking about boiling point for all these, I have to think about how easy is it to hydrogen bond. So with the water example here, I have my partial negative on the top versus my partial positives on those hydrogens. And so with this whole thing, I can have water interact with itself from all angles as long as it's oriented in properly. In methanol, I can only hydrogen bond with this part of the molecule. And so this part of the molecule, it's harder to get to, so the boiling point isn't going to be as high as water. The same goes for ethanol. However, when you have something that are similar looking, so methanol versus ethanol, then I have to think about other stuff like molar mass. I can also think about the polarizability of the electron cloud when it comes to moving electrons to make something even more dipole or not. So for example here, I have more electrons in this molecule, and so I can skew this temporarily more, dipole on the OH over here. And so if I were looking at all these boiling points, it makes sense that water would be the most because it's very easy to hydrogen bond. Then ethanol would be next because it has a more polarizable electron cloud. And then methanol would be last. So the boiling points of these, in case you're wondering, water is 100 degrees Celsius, methanol 64.7, and then ethanol 78.4. These are all approximate. Cool. So again, hydrogen bonds are hecka strong in water. Very easy to hydrogen bond in any direction in 3D space. Methanol versus ethanol, not so much, so that's why they're lower than water. But then ethanol is going to creep up because of, the electron polarizability, electron cloud. Cool. Now, melting point, it also relates to the interactions for IMFs, but melting only rearranged slightly. It's very subtle. And I'm going to re-emphasize that in the drawing on not the next slide, but the following slide. So property stuff, make sure you could draw those particle diagrams. I said that in 3.1. Make sure you could draw those pictures, And so we talked about these solids already. Ionic solids are with our different ions. Our covalent networks are the ones with covalent bonds that we're going to talk about a little bit more in this section. Molecular solids will also, again, I already briefly talked about earlier, talk a little bit more. And then alloys or metallics, we got our metallic bonds. Okay. So, before I talk about properties of solids here, we have our solid, liquid, gas. So, I said earlier that we were talking about melting point between solid and liquid when it comes to the difference between solid and liquid. The IMFs are, again, very weak overall compared to ionic bonds, compared to any other kinds of bonding, which is why their melting and boiling points are really low. When you're looking at solid and liquids, the arrangement of atoms is very different. Well, in this case, this is just generic atoms. I should be drawing molecules, but whatever. So if I think about a molecule between solid versus liquid, they barely look any different in terms of how they're interacting. So solids, they're still interacting in an IMF. They're just, these ones happen to be next to each other. But then in liquids, they're more flowy because a liquid is like that. And so for IMFs, well, again, it's not a very strong force, so the melting point for IMF, so for covalent compounds, is going to be very, very, very low. So they're soft in general. If I happen to touch it without hurting myself, they are very soft for our covalent guys. And then again, they have low melting point, low boiling points overall compared to our all other kinds of compounds because the IMFs are overall very weak. We have our melting point is very subtle, like I said here. And so that's why the melting point is super, super, super low. Boiling point, not so subtle, liquid versus gas. Gases are farther apart, so you want to be careful about that. They don't conduct. We talk about this last section where they can't, molecules can't transport electrons in the ways that ions can, so that's why they can't conduct. And then vapor pressure. So we'll talk about vapor pressure more in the gas unit, but, you know, it does get affected by IMFs. Cool. This is a random thing that I've seen mentioned like once or twice from College Board, so I figured I'd introduce it. So amorphous solids are things that don't have an order. Their structure is disordered. So glass, here's an example of glass, and you can see that glass is made out of covalent bonds here, like between oxygen and silicone. Then you also have charged atoms on this, like this oxygen here, and then it interacts with either calcium or sodium ions, and so you have some, you know, ionic bonds or ionic interactions. It depends on how close they are. And then you got covalent bonds too. But look, they're not in any particular order. They're very, very randomized. And so they're just disordered. Hardcore. And they cool really quickly. That's just a random property to know. So there we go. Crystalline solids. Crystalline solids are based off the solids we've already talked about. Now, this is the bigger category of solids. So like this is solids, random. These are not random. They are patterned in some way. So for metallic solids, we got metallic bonding. Alloys, we also have metallic bonding. Ionic solids is ionic bonds. Molecular solids are IMFs. Covalent network solids are covalent bonds. So this is stuff I've already mentioned previously. All of these have some kind of regular repeating pattern. Not hardcore, but there is some patterns to it. So like molecular solids, for example, there's partial negatives and partial positive sides, and so those are going to have somewhat of a pattern, not a perfect pattern versus like ionic like this. You might run into the term unit cell. It is the smallest repeating unit of anything that repeats in general. So it's just going to repeat. And then we have the crystal lattice, which is how it's arranged. So again, like in this case for sodium chloride, it's arranged in a nice box. The stability varies depending on which it is, because some are stronger than others. So crystalline solids, some of this is review, some of this is new. So we talked about metallic solids already. This is recap. They're good conductors, they're malleable, they're ductile. Remember that metals are positive, and so there's repulsion between the metal atoms, or metal ions in this case, and so that's why they're malleable and ductile, because it's very easy to bend them versus other stuff. Then it's a good conductor because electrons can flow freely. That's how our wires work. So we have electron C model, aka the electrons are just moving around, aka they're delocalized because they're not in any particular atom. They're just flowing. Alloys are made out of metal. They're still metallic bonding. There's the two we learned earlier, substitutional versus interstitial. They're just metallic solids like any other metallic solid, except we have substitutions or interstitial. So same properties as before with the metallic, so make sure you can apply those properties to alloys. All right, ionic solids, again, recap, we have our positive and negative. They're interacting in an ionic bond. These are electrostatic forces. Make sure you remember that. Coulomb's law is a big part of why they're super strong. Talk about which ones have bigger melting points or boiling points based off that from the previous unit. And so then we have our attractions. That shows, again, potential brittleness or crystalline structure and whatever. Now, if you take higher levels of chemistry, you'll learn about this thing, this simple unit cells, the thing I mentioned earlier. And so if you get into hardcore chemistry, you'll learn about these different kinds of ionic solids. In this class, we do not need to know the different kinds of unit cells. Again, it'll be future higher chem classes if you decide to take that. If ions are flowing, they can conduct. As a reminder, they can conduct in two scenarios. We got our liquids, we got our dissolved in solutions. If they are at lattice points, so you don't hardcore need to know this, but like we have these lattice points here. They're just at the ends. And so, like I said last unit, make sure you know the properties because of Coulomb's law, like high melting boiling point, that kind of thing. Cool. Molecular solids. We have to think, what are they made out of? So we have our atoms or our molecules held by IMF. So you could see this, for example, is water. These are both water. And so you can see in 3D space how that would look like. So you could see kind of a repeat of how that would be in space. Same goes for over here. And so there's this nice pattern to it. And so there is a pattern to our, stuff, like ice, for example. Now, remember, IMFs are weak. In general, we have relative forces in terms of like hydrogen bonds are stronger in general compared to like LDFs, but overall they're still weak compared to like ionic bonds, for example. Now, because IMFs are weak, let's think about these properties. Solids, are they soft or hard? Melting point, is it low or high? Conducting electricity, yes or no? So think about that for a second and then I will answer. So solids, they're going to be soft because IMFs are weak. If they were strong, then it would be harder, but they're not. Our melting point's going to be low because our IMFs are weak. These are the things that are quote-unquote breaking. We're breaking the IMFs, and so those interactions are going to be broken, and so that's how you melt and boil them. And then they don't conduct electricity because electrons are not free-flowing easily to transport them. They're only partially charged, so the electrons are not going to easily transport. Examples of molecular solids: ice, sugars, dry ice, which is just CO2 in solid form. Yeah. Alrighty, covalent network solids. So, as the name implies, it has the word network. It's large, covalent bonds. They can come 2D or 3D, depending on if they are flat versus more 3D shaped. So the two biggest examples you need to know are diamond and graphite, which we'll talk about in detail soon. Now, if I were to compare this to molecular solids, so comparing it to this, do you think that based off what molecular solids are held together by, are covalent networks going to be softer or harder compared to molecular solids? And then are they going to have lower or higher melting points compared to molecular solids? So think about that, and then I'll answer in a bit. Alrighty. So they are going to be harder compared to molecular solids because they're held together by covalent bonds. So since they're held together by covalent bonds, instead of an IMF, it's going to be harder. And then in terms of lower versus higher melting point, it's going to have a higher melting point because they are covalently bonded. Bonds are stronger than IMFs. So like I said, the two examples you should know for covalent network solids are carbon and graphite. So both of these are made out of carbon. Cool. And so let's talk about each of them. So first let's go graphite. So graphite are in these rings. So you could see these rings here. And so ring, 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 ring. It's just going literally. These are all carbons. Cool. And so we have sp2 hybridization on all these. You could see here 3 electron domains, hence sp2. There's pi bonds related to this. If you take higher Gen Chem stuff, you'll learn about pi bonds. And so within these rings, the electrons can be delocalized in some capacity. So they can be a little bit moving within this ring. Now, within this one layer, so I'm not talking about the multiple layers yet. Within one layer, do we have strong or weak forces? Think about that, and then I'll answer. So within this layer, we have covalent bonds. Well, covalent bonds are strong, so therefore it's strong because it's covalently bonded. Now, between layers, these can interact in some capacity. They are not bonded. They are layers. So when you're writing, you have layers of graphite. So between layers do we have strong or weak forces? Think about it, and then I'll answer. Alrighty. So between layers, we have interactions, but not bonds. We have interactions between one layer and another. These interactions are LDFs, specifically, if I wanted to mention what kind of IMF this is. So these are London dispersion. And so the electrons can make partial negative and partial positive sides, and so they'll interact between those two layers. Last thing, based off the two answers above, is this soft or is this hard? The answer is soft, because we have IMFs. That's it. Cool. Okay, diamonds. So diamonds come in this 3D pattern. So you can see it's kind of like a tetrahedral shape, and then it'll keep going and going until you reach whatever edge that you're at. And so we have a crystal structure called a diamond cubic. Again, you don't hardcore need to know these unit cell stuff. That's just what it happens to be. So we have this crystal 3D structure. That's all you really, really need to know in terms of how the structure looks like. We have sp3 hybridization, because if I looked at, for example, this one, I am in a tetrahedral. I have my 4 electron domains. Now, obviously, if you're at the very edge of a diamond, you're at the edge, so you can't show that. But in general, you're sp3 hybridized. It is a good insulator. If you wanted a very expensive insulator, it is good. And based off comparing between the previous example, diamonds, are they soft or hard? Now, because it's 3D, covalently bonded everywhere, it would be harder. Now, obviously, I could just answer that based off, like, experience. Graphite, you write with it in a pencil, so you know that's soft compared to diamonds. They're hard as a rock, because they are rocks. And so, yeah. But if you had 2 different examples, make sure you can justify why. So You know, this is a crystal structure of only covalent bonds versus this one is layers where there are covalent bonds in a layer, but each layer is only interacting with an IMF. So just be mindful of the reasons why, not just based off, you know, life. So here's a flow recap thingy of the different solids. So we have amorphous, which is the disorganized one, and then we have our different crystal structures. Now, again, know your properties or why. If you're still kind of confused about the different properties and why, honestly, College Board has a good resource for this. I have it on the class website listed here, so you just have to go to Unit 3 specifically. If you scroll down to 3.2, you can really see the nitty-gritty on reasons why. And you could do this for any section. I have all the sections with the details on what you need to know in the section there, so you can always recheck those in case you're lost. Alrighty, so there's a chart to fill out. And so you need to know what kind of unit particle there is. So my hints are here. You list either ions or atoms or molecules, stuff like that here. And then the forces between. Talk about specific attractions or talk about specific bonds or particular IMFs. Be very specific on what forces are between these particles. Name some basic properties. Again, you need to know why, but just listing the basic properties in general is good. And then any examples you can think of. There's a million examples you can have. So try to fill out this chart because, again, this is based off your knowledge. And then we'll check answers in a few moments. So pause the video. Alrighty. Boom, here's our answers. There's not much for me to talk about because, there you go. Depends. Yeah. If you're confused about these, make sure to ask, especially the whys for the properties. Cool. All right, another quick practice. Here's a your turn. This is an example of one part of an FRQ. So read it to yourself. Try it out. Alrighty, answer. Boop, boop. So you're drawing something like this. Now, obviously, it's in 3D where you would need to show, cube, but you can't really show a cube. So you could draw at least a flat layer. And so make sure when you're drawing, like I said here in the highlight, you're labeling it. Now, you don't get colors while you're doing the AP test. So you want to make sure to emphasize, sections and whatnot. In terms of your explanation, you got to use Coulomb's law. So mentioning how opposite charges attract, how close things are getting, just make sure you use the correct terms. We've already talked about this a million times. Be sure you could do it. All right, that's it for me. Bye.